Hey everyone, welcome to 1.4. It is fun with composite functions time. So we're going to jump over to this page first. And just want to remind you about a couple things dealing with domain that you've probably seen before. This should have been done in Algebra 2. So just some real basic combinations for some algebra properties. So if we have one function that represents x squared, we have a different function for the square root of x plus 1. If we were to add those two functions together, not a whole lot you could do to simplify that, but we're just going to write it out. And so the idea is we want to come up with domain. If you could simplify this, we want to come up with the domain before you simplify, so that we don't get rid of anything that we might have needed to take into account. So that would be the setup. So as we look at this, there's no fractions on this, but the only limitation we're going to run into is the square root function. And as far as that guy goes, just remember that whatever is under that square root must be greater than or equal to 0. And so if I solve that little inequality, then we get our domain, which is x is greater than or equal to -1. Jump down to this one. So we got the fraction. So we're going to put the f of x function on top. And square root of x plus 1 on bottom. Not going to be a whole lot different than this one, except that the radical is now in a denominator. So the one slight change on that is now that it's on bottom, it can no longer equal 0. So it simply has to be greater than 0, not greater than or equal to 0. So if we solve that, we get our domain of x is greater than -1. And one last one over here. So now we're putting the radical on top. We got the x squared on bottom. And so two things we have to take into account. On top, we know that whatever's under that radical has to be greater than or equal to 0. And if we were to solve that, then we got x is greater than or equal to -1. However, on bottom, we know that our x cannot equal 0. So we have to take both of these ideas into account and just state one domain that would satisfy both scenarios. So it's got to be greater than or equal to -1. So it can go all the way up to 0, but not including 0. And then we can union that with 0 to infinity. And so that would be the best way, that would be the best way to state the domain for that last one. Okay, so let's take a look at some composite functions here. So composite functions, just putting one function inside of another. There's a couple different ways we can write this. This is the sort of the common notation that we're going to see in our book. The other way you could write something like that, so if we say f of g of x, the other way that would look is like this right here. All right, so the g function is inside of the f function. And so here's our f function defined right here, 2 to the x power. Here's our function for g. And so we're going to do some composite stuff on those and put one inside of the other. And so they're just showing you both scenarios here. So this is the case where we are putting this function in for that x right there. And that's what creates this setup. And then on the other one, we're putting the f function inside of the g function. So we're going to take 2 to the x and put it in for that x right there. And here's what that would look like. So these are the two different functions. And so the one thing they were asking us to do on this one was just basically prove that they're not equal to each other. And so clearly we can see that these are not the same two results. If we were to graph them both, also clear that they are not the same two results. So let's try a couple of these on our own here. So always a good time to pause the video and try a couple of these ahead of me if you want to. We're not going to do both of these for all three. Let's just try a couple examples here. Let's try this one because we got the fraction going on, and that always creates an issue for domains. So I definitely want to give this one a try. So let's do this scenario right here. So we're going to take the g function and plug it into the f function. So we're going to take 1 over x and plug it in for that x right there. So we're going to have 2, and then we're replacing x with 1 over x squared. And so that's what that setup would look like. As far as domain goes, just recognize the only issue here is we can't have that 0 on bottom, right? So it would be everything except 0. If we were to state the domain on that, we would say something like it goes from negative infinity all the way up to 0, non-inclusive, and we would union that with 0 to infinity. So that's what that would look like. You could simplify this if you want to. So we could say this, if I distribute my 2 here, I'm looking at 1 over x squared, which could just be written as 2 over x squared. And so this would probably be the best way to leave it in its most simplest form. So this is a case where it really wouldn't have mattered if we took the domain from this or from this. We'd get the same domain, but typically as a general rule, definitely want to take domain from the setup, not from your simplified result. If we were to go the other way with it, and if we were to go after this model and plug the f function into the g function, so if we were to take 2x squared and plug it in for this, now we're going to be looking at 1 over 2x squared. So that would be our setup and the result. Really nothing we can do to simplify that. And based on this scenario, this would actually have the same domain as this would as well. They would not always have the same. It's just coincidence in this case. Let me give you one more so we can deal with the square root. So if we were going to go first after this model and take our square root of x and plug it in for this guy right here, so we'd be looking at the square root of x plus 1. So that would take care of this one, and there's nothing you can do to simplify that any further. So we would just state the domain, which, as you guys have already seen, would just be the x's that are greater than or equal to 0, since we got the square root. If we did go the other way with it, we'd be putting the x plus 1 in for this x. So it would look like this. So that would be our setup for this model right here. And just like we've already seen, we take whatever's under that square root. It's got to be greater than or equal to 0. And if we solve it, we have our domain. So let me jump over to the next page. So for this one, now we are looking at decomposing functions. So they're already giving us the final result, and it's our job to figure out what was g of x and what was f of x. So what went into something else. So you can see right here, those x minus 5s could be replaced with just x to create an exterior function. So we know that interior function could just be g of x. And that's what these guys are telling you down here. But I'm going to kind of lay it out for you so you can see it. Right? So if I let the x minus 5 represent g of x, so that's going to be our interior function, and then the overall function, that whole exterior function, is just going to be 2x squared plus 2x. And then you can always check it to make sure that that fit this description right here, and you can see if I were to take x minus 5, put it in for him and him, this is the look that we would get. Right? And so again, we could do the same thing right here. So commonly what you're going to be looking for as far as the interior function goes is if you have something in parentheses or something inside of a radical, or it might be something on bottom of a fraction, whatever you could identify as sort of a separate function usually is going to be your winner for that interior guy right here. So again, on this one, I can take the x squared minus 3, which is under the radical, and we can treat that as our interior function. right? And what was that plugged into? So that f of x function, the exterior, would just be the cube root of whatever. So in this case, cube root of x. So you can see if I were to take this and put it in for that x right there, this is the look that we would get. Okay, so if you want to try a couple on your own, here's a couple examples for you. So I'll do these real quick. Again, you're looking for parentheses, square roots, fractions, things like that should guide you towards that interior piece. So again, I'm going to let the denominator, x squared plus 1, represent that interior function. And what was that plugged into? So that exterior function can just be 1 over x. Right? So this is the overall look, and this is what got subbed in for that x right there. And then again, those parentheses kind of tip us off as to that interior function. So we're going to let g of x be the x squared minus 1. And you can see it might have been more clear had they put parentheses here too. So now it's super clear. And what was this subbed in for? So we always put an x where we see that interior function. So we would say negative 2 and then x to the third, and you don't need the parentheses on that, but it's okay to have them, plus x. Right? And so here's the exterior function that this got subbed into. All right. So we got to see something here on the next page before we jump into example 7. So let me show you this idea of an implicit versus an explicit function. Kind of a lot of vocab words for you, but I'm going to put it in real simple words. When something is defined implicitly, this is where, and this is something that I really wanted to throw this in because it comes up in our beginning calculus stuff in chapter 2. So anyway, so if it's implicitly defined, it's one where the dependent variable, that's our y, has not been given explicitly in terms of the independent variable. Really simply put, here's my words for it, you don't have y by itself. All right, so that's the idea if something is implicitly defined. Explicit just means you do have y by itself. So here's just a simple example, like the equation of a circle, x squared plus y squared equals 4. So this is implicit. This is defined implicitly simply because we don't have y by itself. If you solve for y and get y by itself, here's the exact same function, but now it's written explicitly because you have y by itself. So, and that's kind of all that is. Would fail the vertical line test, which is why I wrote that it's not a function. And then let me give you one more example. So again, here's a function where it is implicitly defined because we have the variables on the same side. If we were to go through and simplify this, so I took this guy, which is a perfect square, I factored it, and I rewrote it as a quantity squared. Right? So this is the same thing as this. This is just like sort of the factored version of it. Square root both sides, and you get this look right here. Get y by itself by subtracting over the 2x. And you got the two different looks. So one for the positive and one for the negative. Right? And so these guys as written this way are now explicitly defined because you have y by itself. Right? Even in this form right here, it's still implicit because both variables are on the same side. So let me jump over back to this guy. So what they're asking us to do with this is they are giving us a function that is implicitly defined, which is typically not the way we're used to seeing them. We usually get y by itself, and they're just asking us to describe what it would look like. Well, oftentimes as it's written in this form, it would be hard to identify what the graph would look like. But if we solve for y, get y by itself, and this is the same one that I just did on the previous page, I basically end up with two parallel lines. All right, these were the two results that I got from my work on the previous page. And so now when I have them defined explicitly, it's much simpler to describe what this graph would look like because this is what we're used to seeing. All right, so we can try that with a couple of these guys. Always welcome to work ahead of me in these. So let me just start with 14. So if I was looking at this one, let me just add the y squared over to the other side. So it looks something like that. Now we can square root in order to get y by itself here. So square root both sides. As you guys know, we always throw in our plus or minus whenever we do that. So now if I were to graph those, what would that look like? If I just said graph y equals x, right, we know it would do something like this. It would go up 1 over 1. If we graphed y equals negative x, it would go down 1 over 1. So really we're just looking at two perpendicular lines here. Right, is what that would be. One with a slope of positive 1, the other with a slope of negative 1. Let's jump over to this one. Again, just want to get that y by itself. So we're just going to factor here. This is the same type of trinomial factoring that you've been doing for years. Ignore the y's for just a minute. If I just had x squared minus 5x plus 6, and I said to factor that, well, we'd have x minus 2 and x minus 3. So the only difference on these guys is with the little y squared at the end. All that means is we got to attach the y onto our factors. So it would look like this. Now we can solve these guys separately. So I'm going to set each factor equal to 0 and solve for y. So if we did on this one, subtract the x, divide by negative 2. And it would look like this. And do that for the other guy. And we get 1/3 x. So now we just took this implicitly defined function, and we could now graph it pretty easily by just graphing those two lines. Would actually give us that function right there.